your lesson on measuring correlation. This is an important part of statistics, and it deals with bivariate data, which is data that has two variables. We have looked at univariate data, which has only one variable, but correlation is a measure of how one variable, which can be represented on one axis, correlates or has a relationship with another variable on the other axis, and often this is done through a scatter plot. Here are some interpretations of correlation. Here you can see scatter data, which is going in a positive direction in all three of these. Positive meaning that as one variable goes up, the other one goes up as well. So you can see all of these are rising. They're all positive correlation. This is strong. The correlation is strong when the points are almost nearly linear, and when they're spread out more, it becomes moderate or medium correlation, and then weak when they're spread out even more. Here we see the same thing in a negative direction. As the x variable goes up, the y variable goes down, so it's negative. And again, we have strong, moderate, and weak correlation. Here's an example of something we can check correlation for. The two variables here are the total number of vaccine doses given to infants before the age of 1, and the second variable is the IMR, which is the infant mortality rate, meaning the number of infant deaths per 1,000 births. So we're going to try to find a correlation here. There's all these countries in the world, and it shows us how many vaccine doses they give their infants, starting with Sweden at the lowest here, in Japan, Iceland, and so on. And then at the highest number of vaccine doses is the US, 26. And then here we have infant mortality rate. And you can see in the US, lots of vaccine doses, but also a high infant mortality rate. And in Sweden, the opposite. So let's check for a correlation by looking at the scatter diagram. So here's the scatter diagram for that data. Here we have vaccine doses on the independent axis and infant mortality rate on the independent axis, and we can see the scatter diagram looks like this. It looks as if when vaccine doses go up, infant mortality also goes up. We have a positive relationship there. So the correlation looks positive, and it does look like it's moderate, maybe weak, but there is some correlation there. There definitely is a trend in this data. But one thing to consider that's important when we look at correlation is, does one cause the other? So just because we see a relationship here doesn't necessarily mean that vaccine doses are the cause of this rise. There might be other variables that are doing this. So that's something to be very careful in when analyzing data this way. All right, looking at these three, we've been using the words strong, moderate, and weak to describe correlation. However, there is a numerical value assigned to giving the strength of a correlation. Please take a look at these three scatter plots and look at these values here. Decide which values here you think match each of these. There's one extra value here you will not use. Okay, hopefully you made this choice. When we see a strong correlation, the number is a higher value, 0.9. Here's 0.85, and here's the weakest of these three, so 0.8. All of them are positive, so they're all positive numbers. So we've been talking about linear correlation mostly, which means correlation of points that seem to follow a linear trend. However, scatter data can often follow a nonlinear trend, such as this. So we can have linear correlation or nonlinear correlation, and both of these we can find an equation or a function to match that data. So you know, when you're working on your IA, you will definitely create a scatter diagram at some point, looking at connections between data, and you may have to even make a function to match the data. So remember about linear versus nonlinear correlation. Here's perfect linear, and here's perfect nonlinear, and we can see that's quadratic for sure. Here's another example. We have this data. It's been graphed on a scatter plot on a calculator. We can see the scatter plot looks like this. We can describe that as strong positive, but let's add another word now to our description, which is linear. We've just talked about. So when you're describing correlation, try to use three descriptors, and one about the strength, one about the direction, and one about the trend of the data. A little side note, in 1956, Australian statistician Oliver Lancaster made the first convincing case for a link between exposure to sunlight and skin cancer using statistical tools including correlation and regression. Until then, we didn't quite understand the impact of UV rays on our skin. So now the key point for this lesson, measuring correlation. There is a measure for correlation, or linear correlation. It is called the Pearson product moment correlation coefficient. It also is known as the R value, and the value R can take is anywhere between -1 and 1 inclusive. It was created by Carl Pearson, who lived in these years, who is the founder of the first University of Statistics department at the University College in London in 1911. R values, when they have a value of -1, that shows a perfect negative correlation. 0 is a no correlation, and R equals 1 is a perfect positive correlation. For example, R equals 1 here, perfect positive. No correlation, R equals 0. Perfect negative, R equals -1. So you know, when the absolute value of the R value is between 0.25, we call that a very weak correlation. Between 0.25 and 0.5, a weak correlation. Between 0.5 and 0.75, a moderate correlation. And between or greater than 0.75, we say it's a strong correlation. Let's take a look at a few examples. Here's one, weak positive. It has an R value of 0.3. Here's another, strong positive. The R value of that scatter data is 0.9. Here's moderate negative, R value of -0.6, so moderate. And here, try these. Looking at all these, see if you can pick the correct answer to show all these R values. Okay, the answer is this. We go from perfect positive to perfect negative, and we have 0 in between. Try here as well. What do you think the R value is here? That one is 0.7. How about this one? That one is -0.3, weak negative. Okay, let's do another example. It says here, a school basketball coach kept a record of the number of games played and the number of points scored for 7 basketball players. So we have 7 players. Here's the games they played, and here's the points they got in total over the number of games they played. We're going to see if there's a relationship. In other words, as a player plays more games, do they get more points? Hopefully that is true. Let's take a look. So I'm going to enter that in the calculator. So here's my calculator. I'm going to turn it on. Anytime you're doing statistics on the calculator, you press the stat button. And anytime you want to enter data, you're going to press number 1, edit. To make this quicker, I've already entered this data. However, if you had other data in here and you want to clear it so that you can enter this data, you would use the arrow, go up to list 1, press clear, and then enter, and that list would be clear. And then do the same thing with list 2. Clear, enter, it would clear it out. But I already have the data, so I've entered in this data in list 1, this data in list 2. I didn't include the totals because that's not part of the data set. Okay, so let's see how we calculate an R value on here, because the instructions here was use Pearson's correlation coefficient to determine the strength of the correlation. So let's check. Again, I'm going to press stat, and this time I'm going to use the arrow and go over to calc. We've used that before to figure out one variable statistics, but now we're trying to find an R value, which has to do with linear regression. Linear regression is creating a line of best fit for data. So we'll look at that next time, but let's look at the R value. The R value can be found in there. Okay, let's try. So press number 4 or select linear regression. And here you're going to put the list. So by default, it has list 1 and list 2. If you ever need to enter lists, you can press second and one of these numbers. You can see list 1 is above number 1, list 2 is here, list 3. So list 1 and list 2 is what I want. I'm going to arrow down to calculate. And hopefully I'll see the R value because that's where it's supposed to show it to me. So I've pressed it. I see some kind of equation here. We'll talk about that next time, but I don't see an R value. There's a problem. Maybe yours calculator is doing the same thing. There's no R value. This is something important to remember because by default, the calculator has something turned off, which gives you an R value. Here's how you will turn that back on. So press mode. And in mode, you're going to go to the second screen. So I'm going to arrow down to the next screen. In the second screen, if you look in the middle, it says Stat Diagnostics. You need to go there and turn it on. So I'm going to go Stat Diagnostics, go to on, press enter. I'm going to get out of this menu by pressing second quit. So now my stat diagnostics are on. So when I do those steps, it should show me the R value now. So stat, calc, number 4 is linear regression. So I'm going to press 4. List 1, list 2, everything's okay. Calculate. Now I should see the R value because I turned on my stat diagnostics. And there it is. So we have the Pearson's correlation coefficient right there, 0.957. Let's check here. 0.957. All right. That shows a strong correlation, strong positive correlation. So as players do play more games, they have more points. Let's check the scatter plot for that. So I'm going to do graph. Hopefully my stat plot is on. Let's double check. Stat plot on. Great. So I'm going to press graph. I see no data. So you press zoom and go to zoom stat. It will change your window so that the window shows you the data you've entered. So number 9, zoom stat. Now I see my data. Oh yeah, and I can see that there's definitely a strong positive correlation there. Okay, great. So that's how you find R value in the calculator. Now let's look at the opening problem. Back to the vaccine doses and infant mortality rate. It looked like it had a strong or maybe, sorry, a moderate or a weak correlation. I calculated the R value for that as well. Here it is. And the R value is 0.7. So that's actually close to strong, but moderate. That's a moderate positive correlation. So there's some kind of relationship there. That's interesting to see. Okay, so moderate positive linear correlation. Okay, if you're interested, here are the actual formulas that are used to calculate the R value. You can find lots of material online about this if you want to research it. For this course, though, on exams, you are allowed to use the calculator. So as I've shown you, you can find the R value like that. However, some students choose to use these formulas to find the R value on their IA, so it's something to think about. TOK question, what is the difference between correlation and causation? So we mentioned that at the beginning. It's important to know that to what extent these different processes affect the validity of the knowledge you obtain. So for example, you see a correlation and you have some knowledge from that, but does that knowledge lead you to think about causation or not? So just because two variables are correlated does not mean that one causes the other. Let's take a look at some examples. Here's a funny example. In the beginning of this chapter, we saw that hot drinks consumed in the UK is linked to the sales of socks. So does one cause the other? I don't know. Adam saw this information and he thought his wife was spending too much money on socks. So to try to stop this, he said she should drink less tea per day because he said, well, tea drinking causes sock purchases, and that's kind of an erroneous conclusion to make. So the main thing to remember here is a correlation between two data sets does not necessarily mean the change in one variable causes the change in the other. Let's look at some other examples like that. Here we have in black the number of people who died tangled in their bed sheets, and in red the per capita cheese consumption. You can see as one goes up, the other goes up, and there's a very close relationship. But that would be a crazy conclusion to make, that eating more cheese causes you to die by tangling yourself in your bed sheets. All right, so that is definitely correlation, but not causation. Here's another one. We have employees getting training, and then the price of production. So this correlation is strong as well, but this could be definitely causal because as employees get more training, then the costs of producing things at this factory, for example, should go down. That makes sense. Here's another one. Here's lemons imported to the US from Mexico, and here's traffic fatalities on highways. So as more lemons come into the US, there's less traffic fatalities. Strong correlation, definitely not causation. That would be a strange causal relationship. And on this problem here, just decide in A, B, C, D if you think there is a causal relationship. Does one cause the other, or is one an effect of the other? Okay, check your work. And let's end with this statement. Here's another correlation versus causation situation. We see ice cream sales during the year going up and then down, and highest in the summer. And also shark attacks going up and down. Oh wow, there must be definitely correlated. As we eat more ice cream, there's more shark attacks. But does that mean ice cream eating causes shark attacks? Definitely not. It's just a coincidence because they both occur in the summer. Here's a joke. If you're laughing, you understand this point. Please do the practice assignment. You can do it.